Guglielmo Lacorata from Ismar, Roma, and I've been working in Lagrangian transport and dispersion from several years. I come from theoretical physics, and in the course of the recent years, I have applied some of the knowledge in the dynamical system theory for the study of Lagrangian transport and dispersion processes in geophysical flows. So this talk is just about this topic, as the title says, and we will see some theoretical aspects and recent applications during this talk. Some of the main points will be a brief recall of a comparison between scale-dependent and time-dependent statistics in the description of relative dispersion. Another point will concern the use of the finite scale Lyapunov exponent as analysis techniques to study the general characteristics of relative dispersion in the global ocean. And then we will see also an application of the so-called second kind finite scale Lyapunov exponent as a key element to define a Lagrangian validation methodology of ocean current fields. Okay, let me first thank and mention my main collaborators in these last years. As you can see, some people come from Ghost Group, some are from a university, someone from the Stazione Zoologica of Naples, some from the L'Aquila University and La Sapienza, and let me mention two direct collaborators of mine, Luigi and Raffaele, former contract researchers at CNR. And you see here below some of the international research programs that helped to financially support this kind of activity in these last years. Okay, I guess you have heard and seen these things many times before, but let me recall briefly the basic elements of a dynamical system. When we think about a dynamical system, we have in mind equation system of ordinary differential equations with a set of initial conditions. We assume that state vector can be suitably defined with having n dimensions. We assume that the solutions are bounded in the phase space just to ensure a physical sense to the model, to the system, and together with the solution of the dynamical system, we always consider the evolution of an infinitesimal perturbation described by the so-called tangent map associated to the dynamical system. Tangent map defined in terms of the well-known Jacobian matrix derived by the time evolution operator. Okay, let's focus more closely to conservative dynamical systems. Here, the basic some basic concepts and definitions are summarized. We assume the uniqueness of the solutions, of course, because we are considering deterministic dynamics. As anticipated before, all motions are bounded in the phase space because we want to consider only finite energy systems. If the system is conservative, this means that the divergence of the time evolution operator is null. This means that phase volumes are preserved. In general, there are n Lyapunov exponents for an n-dimensional dynamical system. In a case of a conservative system, the sum of all Lyapunov exponents is equal to 0. And the positive sign of the maximum Lyapunov exponent is the mark of the presence of a chaos in the system. Then here we remind the formal equivalence between a Lagrangian system and an Hamiltonian system, with thanks to the formal equivalence between the stream function and the Hamiltonian function. And last, this is I think an important thing to consider, is the time reversal symmetry of chaos for a conservative system. This means that if the system is chaotic forward in time, it is chaotic also backward in time. So if it generates chaotic diffusion forward in time, it generates chaotic diffusion also backward in time. And we will see later how this property can be used. Okay, as far as a trajectory separation is concerned, the first thing to notice is that his consideration is that particle separation substantially depend on the velocity differences at the scale of the separation. And this is known also as a locality property. And this remark justifies the conjecture that the use of scale-dependent quantities is more appropriate than the use of time-dependent ones in the description of a relative dispersion. Here you see the definition of this quantity, known as the finite scale Lyapunov exponent, which was born as the generalization of the Lyapunov exponent to finite perturbations in the phase space. You can see here a theoretical definition of the finite scale Lyapunov exponent, and on the right the operating definition, which takes into account the finite resolution of the trajectories in practical applications. Okay, these are the basic steps to follow to compute the finite scale Lyapunov exponent. Of course, we have a pair of trajectories separating from each other. We define a series of fixed scales, delta 0, delta 1, delta 2, delta n, which differ from each other by a constant ratio rho. Once the series of scales has been defined, the statistics of the so-called doubling time scale by scale is computed, and so the finite scale Lyapunov exponent is formed in the end. Of course, the norm used to measure the separation between trajectories depend on the geometry of the system. Okay, let's take a quick look at the main reason why a scale-dependent description of relative dispersion is needed. Thanks to a test model in which we introduce only two dispersion regimes: a small-scale regime, which corresponds to exponential separation, if you prefer Lagrangian chaos, and a large-scale regime that corresponds to standard diffusion. The discriminating scale separating the two regimes is can be considered as the finite resolution, as a characteristic scale of the flow, for example, due to the finite resolution of the field. If we check this test model by letting the exponential growth rate fluctuate around a mean value, so actually we are considering that this exponent is twice the finite time Lyapunov exponent, because here in this case the exponential separation lasts for a finite time interval. So this exponent corresponds substantially to twice the finite time Lyapunov exponent. Finite time Lyapunov exponent, which is subject to fluctuations around the expected mean value, which is just the maximum Lyapunov exponent. So what does it mean? This means that if we carry out a fixed time average of the separation growth averaged over a large number of trajectory pairs, each realization of the separation growth is characterized by its own exponential growth rate, which is not the same as we have said before, which is not the same for every trajectory pairs. This means that if take the fixed time average of these curves, it may happen that we are mixing together trajectory pairs evolving in one regime together with trajectory pairs evolving in another dispersion regime. And this may easily generate spurious pre-asymptotic scaling laws that actually does not correspond to anything physical. While if we carry out the relative dispersion analysis in terms of the finite scale Lyapunov exponent, we recover exactly the only two dispersion regimes that we have introduced in the test model. So the test model has just only two dispersion regimes, the exponential separation and the standard diffusion, and these two regimes are exactly the only two that we recover with the FSLE analysis. Of course, the relative dispersion process in general has more than two regimes. For example, it may include an intermediate range of scales in which relative dispersion may be turbulent. So these are typical finite scale Lyapunov exponent scalings that can be taken as a reference pattern when analyzing relative dispersion. This is the formula of exponential separation. Of course, that corresponds to an exponential separation in the time domain. This is the scaling corresponding to the Richardson law, which is equivalent, of course, to the famous T-cube law in the time domain. And finally, this is the scaling law corresponding to the standard diffusion, delta to the -2, corresponding to the well-known linear growth of the mean square relative displacement in the time domain. This is a graphical representation of what has been just anticipated in the previous slide. So you can see exponential separation, flat behavior. Delta to the -2/3 is the scaling corresponding to the Richardson diffusion, and delta to the -2 is the scaling corresponding to standard diffusion. Okay, this is a picture representing all possible applications of the finite scale Lyapunov exponent technique, at least to my knowledge. And we will see something about these three kinds of applications. We will see how the FSLE can be applied to study the scaling laws associated to the relative dispersion process, and to the measure of physical parameters associated to the scaling laws of dispersion. And then we will say a couple of words about the definition of an innovative Lagrangian validation methodology based on the use of the second kind finite scale Lyapunov exponent, which allows us to have an objective analysis tool to evaluate the Lagrangian scales of some ocean current field dataset, as we will see later. Okay, this is the reference pattern when thinking about turbulent fluid, which is characterized by having a so-called inertial range of scales inside which we expect to observe the famous Richardson superdiffusion, scaling like delta to the -2/3 inside the inertial range of the fluid, and the other two regimes, as we have anticipated before, the exponential separation at the smallest scales of the system and the standard diffusion at the largest scales of the system. Okay, what is the general procedure if we want to set up a Lagrangian numerical simulation? Let us consider a large-scale domain and a two-dimensional approximation. This means that we are interested in Lagrangian simulation in open sea, far from the boundaries, and over the large-scale domain. The first step is, of course, the retrieval of ocean current data of any origin. This kind of fields can be generated by model simulations or measured by satellite techniques. The Eulerian data, this kind of Eulerian data, of course, is characterized by a finite spatiotemporal resolution. For example, typical values can be a time resolution of 1 day daily fields with a spatial resolution of order 10 kilometers. If we consider only this contribution to the dynamics, this large-scale field can substantially take into account only the large-scale advection, and usually underestimates greatly the small-scale relative dispersion between tracers. How can we evaluate the missing scales of motion smoothed out by the finite resolution of the large-scale model? By comparison with a real ocean drifter dispersion. After doing this, the missing scales of motion can be replaced by a suitable subgrid model, for example, defined in terms of kinematic chaotic models, so that the total field, the coupled field, large-scale component plus the small-scale kinematic component together can take into account with some accuracy both the large-scale advection and the small-scale turbulence. Just to see in some mathematical detail the kinematic field we are talking about. We are speaking about a two-dimensional incompressible flow defined by a stream function of having this form. So not very complicated. And as anticipated before, an interesting aspect of the question. The question is the formal equivalence between a Lagrangian system and an Hamiltonian system, after noticing that the stream function has the role of an Hamiltonian function and the pair of Lagrangian coordinates are equivalent to a pair of canonical variables of Hamiltonian mechanics. Of course, this kind of model, if needed, can be generalized to a three-dimensional version, but in which case the stream function becomes a potential vector having three components, one for each direction, and the velocity field is defined as the curve of the potential vector in order to have a solenoidal velocity field, where the three components of the stream function, the potential vector stream function, have this self-similar form. Okay, this is just a picture to visualize the kind of kinematic fields we are speaking about. This is the two-dimensional version, which is just a lattice of square convective cells. And this is a picture of a three-dimensional version of the field. In the two-dimensional case, the color map is formed by plotting the vorticity field, while in the three-dimensional version, the map is formed by plotting the kinetic energy per unit mass. Okay, let's see some applications in physical oceanography that will be briefly discussed in a while. First, we will discuss the case of the Mediterranean Sea, where Lagrangian numerical simulations were applied to evaluate the survival probability of sea turtle hatchlings during their first year of life. And we will see how the information coming from the Lagrangian simulation is valuable to assess the survival probability in comparison, the survival probability in comparison with the so-called stable nesting sites already existing in the southern part of the Mediterranean Sea. Nextly, we will say something about the Lagrangian validation methodology as a tool for the assessment of the accuracy of numerical trajectory simulations generated from a given ocean current dataset. And last, we will see how systematic finite scale Lyapunov exponent analysis of the large amount of drifter data coming from the provided by the Global Drifter Program can give some kind of universal picture of the general characteristics of relative dispersion for the global ocean. First of all, before using a Lagrangian simulation, of course, the first question is how to set up the Lagrangian model. To set up the Lagrangian model, for the setup of the Lagrangian model, we absolutely need information from observational data, namely from real ocean drifter dispersion. So you can see here the results of the FSLE analysis of model trajectories, which are represented by empty squares, these symbols. Model trajectories which are generated by the Mediterranean forecasting system fields. Then, okay, what we can see from the behavior of the dispersion rates of the Mediterranean forecasting system trajectories only. We see here the effect of the finite resolution of the field, which makes the curve be flat below a given threshold. This threshold is some multiple of the finite resolution grid of the model. While the same quantity, the same dispersion rates computed for the Mediterranean drifters follow another kind of behavior at the smaller, in this small scale range. So depart progressively from the model trajectories and follows a scaling that to the -2/3, which is compatible with the presence of mesoscale turbulence in this range. Well, okay, the conclusion is that the model trajectories, the model dispersion, is significantly underestimated with respect to the real ocean drifter dispersion in the same area. So what can we do to compensate for this energy gap? We can set up the kinematic fields on the small scale range in order to get a final spectrum of the dispersion rates of the coupled model overlapping to the curve corresponding to the ocean drifters. And this is what can be obtained if we extract these important parameters from the drifters, which is an estimate of the mean turbulent energy dissipation, characteristic of turbulent regime. It's a parameter that we use to fit the subgrid model to the data. If we do that, the coupled model, Mediterranean forecasting system plus kinematic Lagrangian model, has a curve of the dispersion rates which practically overlaps to the curve corresponding to the ocean drifter at all observable scales. So this is just the premise to the use of a Lagrangian simulation. Okay, this work was about the problem of range expansion of the sea turtle in the Mediterranean Sea. As we have anticipated before, the set of stable nesting sites of the caretta are located in the southern Mediterranean basin. But nonetheless, these these sea turtles are known for being colonizers, so they randomly try to expand their range by releasing eggs to some random place. And so the question is if this new nesting site is stable or not by self-recruitment. Self-recruitment means that sea turtles, after I don't remember how many years, maybe 10 or 20 years, are capable, don't ask me why, are capable to return back to the site where they were born to release eggs again, and so start a recurrence process. Okay, the stability of a new site depends, of course, on the local climatic conditions, but as we will see, also on the sea surface temperature. The information, the observational information about the new site was that a new site was found in proximity of Ogliastro in Campania, where the local climatic conditions are surely favorable for as a potential new nesting site, but the survival probability after 1 year is almost a zero of the hatchlings of the turtle. How can we assess this? Thanks to Lagrangian simulations of the passive transport of the hatchlings all across the Mediterranean Sea. And these simulations state that after 1 year, almost all hatchlings die of cold. Let's remember that we are speaking about ectotherms. And so once is assessed that with the current climate conditions, considering, of course, local climate conditions and sea surface temperature evolution, a new site is not stable. One question may be how the effects of a possible global warming will affect the properties of a new site. In other words, if a new nesting site is not stable now, will it become stable in the future? And we can make projections about this question, both looking at ensemble forecasts from the IPCC model projections, but also looking at observational sea surface temperature data. And we will see that these two, the observational source gives significantly different information with respect to the model forecasts. Okay, let's see the PDF after 1 year of the turtle hatchlings starting from Ogliastro for 2 different years. In the 2 upper panels, the fatality rate is switched off. So the hatchlings survive independently on the temperature of the marine waters, while on the 2 lower panels, you can see the final PDF if we turn on the fatality rate. Fatality rate that, of course, depends sensitively on the temperature of the sea. The rule that we used is that if the hatchling encounter a temperature lesser than 15 degrees for consecutively, they die. So you can see that if we turn on the fatality rate, only a small percentage of the initial distribution survive. And here below, you can see the map of the stable sites, the stable nesting sites, as we said before. Stable nesting sites distributed all along the coasts of the southern Mediterranean basin. Okay, this is an animation of the numerical simulation of the hatchlings transport. This is a particularly favorable year when the survival probability attained its maximum value, if I remember right, of 3 or 4% of the initial distribution. Okay, you can see the color bar is discriminating between life and death. Death occurs if the temperature drops down below 15 degrees. So when you see the particle color become blue, it means that the hatchling dies. Okay, let's see once again this simulation. Okay, you can see a large part of the distribution becomes blue, except a thin layer here along the Calabria coast. And while if we reply this kind of simulation for another year, which we observe the minimum survival probability, you can see that really all particles become blue in the Tyrrhenian Sea. So in this case, the survival percentage is really at the lowest term is less than 1%. Okay, just to end this topic, as I anticipated before, with respect to projections for the next future, the model, the climate model forecasts that we have analyzed would suggest that a waiting time of the order of 10 or 20 years before the new site in Ogliastro can become stable. But the observational SSST data have a much lower trend, almost 1 order of magnitude lesser than the model forecast, so that the waiting time before the new site may become stable is 10 times longer. So this is just an open question left for future research. Let's go to another application regarding the use of Lagrangian validation methodology that has been applied on velocity field data measured in the framework of measured thanks to satellite-based techniques in the framework of the Globe Current program. What is the theoretical idea at the basis of this approach? Let us consider two kinds of velocity fields. Okay, and so we have two kinds of trajectory evolution, one for each velocity field. Let us consider that the two trajectories start from the same position, so the initial distance is 0. And assume that this quantity, V star, is a measure of the mean velocity difference between the two fields. For example, we can consider the two velocity fields differing from each other only for the spectral content at the smallest scale. So let us imagine that there is a kind of a low-pass threshold scale for which the two energetic spectra are equal to each other at scales larger than L star, and the spectrum, the energy spectrum of one of the two fields is 0 for scales lesser than the low-pass filter. And let us define this E star as the energy content of the spectral difference between the two fields. So this let's on the basis of this argument, we can write the early stage trajectory separation as a linear behavior in time, and the prefactor is reasonably related to the energy gap between the two fields. Okay, let us see how the methodology works first for a test model. A test model is the usual kinematic models, which is, as you can see, it can be used in various contexts. The model has 8 velocity modes. As you can see, the string function is the superposition of 8 terms, 1 for each velocity mode, characterized, of course, by a wavelength, wave number, and the velocity scales that satisfy the Kolmogorov relationship with the wavelengths of the flow, and where sigma n and omega n are the time-dependent perturbation parameters that let the flow be chaotic. What is the result if we carry out an FSLE analysis of relative dispersion, FSLE analysis of first and second kind? Okay, second kind means simply that we are measuring the separation between one trajectory evolving in a given velocity field and the other trajectory evolving in another velocity field. So you can see that the curves below the black one is the relative dispersion rate spectrum of the full resolution model. So the full model, in which we consider all the velocity modes together. The curves below the black one correspond to the finite scale Lyapunov exponent of first kind of the same model at lesser and lesser resolution. So we are eliminating some velocity modes gradually, so to pass from the full model having 8 modes to the lowest resolution model having only 2 velocity modes. And you can see how the finite scale Lyapunov exponent is modified by varying the spatial resolution of the model, while the curves above correspond to the measure of the second kind Lyapunov exponent, which means the Lyapunov, the FSLE of a trajectory pair in which one trajectory evolves according to the 8-mode full model dynamics, which is taken as a reference model, and the other trajectory of the pair evolves in turn according to the following the coarser resolution models. So this small-scale behavior reproduces the delta to the -1 scaling that has been anticipated in the previous slide. This means that the prefactor of this scaling in the small-scale region give us a measure of the energy gap between the full resolution model and the coarser resolution approximation. First element to notice. A second element to notice is a kind of recombination scaling, which is the scale, the separation scale, after which second kind and first kind FSLE overlap. This means that after this threshold scale, the model error in this case due to the different resolution between the two fields, is absorbed by the intrinsic nonlinearity of the dynamics. Okay, let's see this picture applied to oceanographic data, finally. Okay, you can see here the Lagrangian validation applied to globe current data for the Mediterranean Sea. These blue squares are the dispersion rates of the globe current fields without subgrid contribution. The black squares are the dispersion rates of the Mediterranean drifters that we always consider as our benchmark for the validation. The red squares are the dispersion rates of the coupled model globe current fields plus kinematic small-scale field, which gives, also in this case, a dispersion rate curve that is almost overlapping to the dispersion rates of the drifters. One thing to notice in this case is the change in this so-called recombination scale. If we do not consider the small-scale parametrization of turbulence inside the globe current field, this threshold has a certain value near 100 kilometers. If we consider the coupled Lagrangian simulation, considering the globe current field plus the kinematic small-scale field, this threshold decreases to a lesser value, so it passes from something like 80 kilometers to 40 kilometers. So this is this corresponds to a certain gain in the accuracy of the Lagrangian simulation, since the scale after which the model error is absorbed by the intrinsic dynamics is smaller than in the previous case. This is the same picture if in the place of globe current data we consider velocity fields from the Mediterranean forecasting system model. Okay, the picture is qualitatively the same. The only relevant difference, I think, is in the position of this recombination scale. As you can see, in this case, we have a gain by adding the subgrid model to the large-scale fields. In this case, we do not observe any improvement, just because this delta star practically falls outside the resolution scale of the model. Okay, this is a final example referred to the North Atlantic Ocean, which the picture is maybe cleaner than before. And you can see more or less the same behavior. The blue squares correspond to the globe current only trajectory simulation. The black squares are the dispersion rates measured from the North Atlantic drifters. The red squares represent the dispersion rates of the coupled model globe current plus KLM. In this case, the improvement in the recombination threshold scale is even more evident, because we pass from 200 kilometer recombination scale to 20 kilometers recombination scale, with a gain of 1 order of magnitude, which is interesting. And the conclusion is that with this procedure, in general, if we couple globe current fields, globe current velocity fields with a suitable parameterization of the unresolved turbulent scales in terms of the kinematic modeling, the total model has good Lagrangian scales compared to ocean general circulation model, if not better. Okay, let's see another application in which the first kind, in this case, the first kind of finite scale Lyapunov exponent was used to have a picture, to have a global, a universal picture of the characteristics of relative dispersion all over the global ocean. A global ocean that can be subdivided into an 11-element partition on the basis of the value of this quantity, the wind stress curve. So once the global ocean has been subdivided into elements, so into macroscopic subbasins, we can carry out a systematic finite scale Lyapunov exponent analysis of relative dispersion for each of the 11 ocean basins, and this is what comes out. Very briefly, okay, you can see more than one curve for each panel, because we wanted to consider all possibilities between two drifters with drogue and without drogue. So the reference curve in each panel is the red one, which corresponds to relative dispersion between drifters that still have their drogue attached. You see that the appearance of some known scaling regimes, for example, delta to the minus 2/3, which is linked to the presence of turbulence in the system. The mesoscale plateau is present practically everywhere. so exponential separation of particles at scales comparable or smaller than the Rossby radius. And another interesting characteristic is the presence, not everywhere, but somewhere, the presence of this second plateau in correspondence of the so-called sub-mesoscales, which give us an indication about the existence of a dynamics which has characteristic times very different from the characteristic times associated to mesoscale dynamics. But this is still an open issue, and maybe which is of course left for future research. Okay, this is just a picture of the statistics, the distribution of the number of pairs that we have analyzed for each ocean basin, just to see the statistical significance of the computations. And this is, I think, a nice conclusive picture that summarizes the main relative dispersion characteristics observed in all the 11 ocean subbasins, which are listed here. Okay, what is the result? The result is the existence, not everywhere, but where it was possible to observe it, of an exponential separation characterized by a doubling time of less than 1 day. If you consider that these are dispersion rates, so the inverse of a doubling time. So the exponential rates are of the order of 1 day to the -1. So the corresponding doubling time is of the order of a fraction of a day, which is an interesting order of magnitude, because it is close, I think, to the characteristic times of the mixed layer. But we can discuss about this in some other occasion. Then we can appreciate the existence of an exponential separation regime at the mesoscales. And the mesoscales, broadly speaking, at the left of the Rossby radius, characteristic of each ocean basin. Exponential separation characterized by the same order of magnitude of the exponential rate. So as you can see, so the characteristic doubling time are of the order between, let's say, 5 and 10 days. Then there is the presence of a turbulent dispersion regime. Turbulent dispersion regime, I remind you, is where we observe a delta to the -2/3 scaling of the finite scale Lyapunov exponent, characterized by having a turbulent dissipation rate of the order of 10 to the -9 meters squares to second cube. And it is interesting that these all the 11 subbasins display the same order of magnitude of all these physical parameters. In some cases, not always, in some cases, it is possible to observe also standard diffusion. In those cases, where the domain, the spatial domain, is sufficiently wide for the standard diffusion to be observed. And when it is possible to observe standard diffusion, it is characterized by a diffusion coefficient that, again, has the same order of magnitude in all sub-basins where it was possible to observe it. Let me close this chapter with two supplementary checks that we did on the measure of the finite scale Lyapunov exponent on a new set of GPS tracked drifters, which have a resolution and hourly resolution, just to be sure that the results previously obtained are not affected by time and resolution, the time and resolution of the previous drifter dataset that we used in the first place. So the picture is substantially confirmed by analyzing the GPS tracked drifters. And this is just a check about the stability of the result of the FSLE analysis if we vary the parameters of the curve. Essentially, if we vary the ratio between the scales, or if we vary the initial threshold of the initial separation from which the analysis starts. And all in all, let's say that the result is rather robust to variation of the parameters. Okay, last, I promise I am going to the end of the talk. Last, we tried to use the information provided by the finite scale Lyapunov exponent behavior in all the ocean, in particular the finite scale Lyapunov exponent measured for the Indian Ocean, to see if we could say something about the reconstruction of the crash site of this important event that occurred in March the 8th in 2014. Maybe many of you remember about this fact, where the MH370 flight from Malaysia airline disappeared, probably in the Indian Ocean, without leaving any trace. So nothing about the aircraft has been found so far, except for some little fragments of the aircraft along the coasts of Africa. This remains a great open question to estimate the possible crash site of the aircraft. These are all we know about the evolution of the accident. The airplane was flying from Kuala Lumpur to Beijing, but instead of following its route, abruptly changed its route to westward, and then presumably continued to fly towards some kind of Point Nemo, so to say, of the Indian Ocean, just to following a no return back flight, until of course the airplane ran out of fuel and crashed into the ocean. So what do we know about this accident? We know information coming from the Inmarsat satellite that after the airplane, after the last known position detected by military radar on the Andaman Sea, more or less here, the only trace of the aircraft flight, the only trace comes from hourly interrogation of the Inmarsat satellite that almost every hour sent a signal and received in response the reflected signal by the aircraft that is characterized by a peculiar code, so that one can be sure that the signal has been reflected back by that particular aircraft. And this kind of detection position, this kind of position were detected almost every hour until the so-called seventh circle was reached, and there was where the seventh circle was reached, which corresponds to the last response of the aircraft to the satellite interrogation. So after responding for the seventh time to the satellite, the aircraft crashed into the ocean. So we have this information that concerns the probable distance of the crash site with respect to the position, to the projection of the position of the satellite on the equator. And we have another interesting information coming from the maximum flight range that can be estimated knowing the amount of fuel loaded in the aircraft. These two circles have a comparable radius of the order of 5,000 kilometers. And this is more in detail the so-called official search area, which is located around the famous seventh arc circle that we have introduced before. A quick consideration about this fact comes from David Griffin from Cairo, with whom I had a mail exchange some time ago, who states that according to his conjecture, there is an upper limit to the latitude of the crash sites, just because if the crash site were north than 35 degrees south, some of the debris would have certainly touched the Australian coasts because of a bifurcation of the current at those latitudes. But very strangely, very curiously, while something like 20 or 30 items coming from the airplane have been found along the coasts of Africa, nothing was ever found on the coast of Australia. So this pose an upper limit to the latitude of the unknown crash site. What can we do by the knowledge of the drifter analysis? Of course, we can try a simple idea, simplest as possible, rely only on observational data, so the drifter, the information coming from the drifter, use the strategy of backward motion, which means going from known information to unknown information. Possibly check out the methodology on some simplified test, just to see if, at least in ideal condition, it may give some interesting response. And of course, hope for good luck. As usual, we tried the point source reconstruction in this simple model, which has the same form as the kinematic fields seen before, so nothing complicated, nothing strange. In what consists this strategy? Of course, we make first a forward in time simulation of debris spreading, if you want. Debris spreading from this point source forward in time. After a while, the debris will be distributed according to some distribution function, of course. Let us imagine to observe only a small fraction of the debris in 3 independent positions. So here, in these 3 locations, the red one, orange, and yellow, from each of these positions, we can try to trace back the set of tracers, obtaining in the end the distribution corresponding to the red position, another distribution, the orange position, corresponding to the orange starting position, and the yellow one corresponding, of course, to the yellow starting position. It is interesting to note that the point source is located inside the intersection of these 3 backward in time PDFs. So this works in a simplified model. Let's see if it works in this applicative case. What we did, the first thing was to identify drifters passing by La Réunion Island. That is the first place where a debris officially linked to the aircraft was found after something like 508 days from the disaster. In particular, a flaperon, which is a piece of the wing of the aircraft, was recovered at La Réunion Island. So the first thing is to identify how many drifters pass by La Réunion within a given threshold distance, and possibly to exploit these drifters, tracing them back in time to see the possible origin of the unknown debris trajectory. We found 4 drifters responding to these characteristics. Notice that the loss of the drogue occurred very soon after the release, and this is interesting because the ocean drifter without the drogue are a better approximation, if you want, of a macroscopic size floating object, like the piece of the wing of an aircraft on the ocean surface. So let's see what information we can get from tracing back these drifters, tracing back of a time corresponding to the time interval between the disaster date and the date in which the flaperon was recovered at La Réunion. This is the terminal point of drifter A. Not only we have a terminal point, But we can associate to the terminal point an error, a locating error, simply because as a trajectory moves forward in time or backward in time is equivalent, all virtual trajectories starting close to the reference trajectory are supposed to separate from the reference trajectory following the specific property that the finite scale Lyapunov exponent has measured for that part of the ocean. So, in a few words, the FSLE analysis gives us the possibility to estimate the radius of the uncertainty area to associate to the terminal point of a backward drifter trajectory. We did for the drifter A, this is for drifter B, drifter C, and changing perspective, this is the final picture where we put the four drifters together. You can see four different colors: orange, red, cyan, green. The intersection of the uncertainty area is this beautiful white spot. Why, in my opinion, it is an interesting result? Because it is compatible with the upper latitude limit of David Griffin discussed before. It is compatible with other independent estimates of the crash site that I didn't report here, but there is an independent estimate of the crash site coming from a modeling approach by Maximenko and his collaborators, which has a good fraction of overlapping with our white spot. And last but not least, maybe the most important element to notice is this white spot includes the intersection of these two major constraints of the problem, which are, I remind you, the seventh circle, which is the maximum distance from the Inmarsat satellite reached by the aircraft. The intersection of this gray circle with the black circle representing the maximum flight range estimated by knowing the amount of fuel. So maybe it is just a pure chance that our estimate of the crash sites overlaps with this intersection, maybe not, but of course only time will tell if this makes sense or not, and because nobody knows, nobody can tell if there is some chance in the future to discover something about this mystery. Of course, the conclusions are that to Lagrangian data analysis, the finite scale Lyapunov exponent is the optimal indicator to use to have a physical and objective physical description of the relative dispersion properties. As regards to Lagrangian modeling, the multi-scale deterministic chaotic systems, in other words, the kinematic models, are established as the most efficient tools to simulate any regime of turbulent dispersion. So they are particularly valuable in application where they are used as a subgrid parameterization of unresolved velocity modes. Finally, these two techniques, finite scale Lyapunov exponent analysis and kinematic modeling can be combined together to form the basis to define an innovative Lagrangian validation methodology for the evaluation of the accuracy of Lagrangian simulations generated by a given ocean current field. This is a list of main references that contain the topics discussed in this talk. And thank you very much for your patience and for your attention.